All right, that's a Texas way of saying hello. Okay. This work is done by my student, Susav Shrestha, who's in a summer internship, so he couldn't make it here today, and with collaboration with Zongwang Lee, who's at Samsung. Okay. The motivation for this work came from various reasons. Obviously, Samsung produces SSDs, and they're trying to look at how to use SSDs efficiently in machine learning applications. And so part of the work came from there, okay, part of the motivation. So just to give you a brief background, the keynote touched on a lot of these issues here, but information retrieval, for example, you go to Google and type a query, you expect to get the document that's relevant to your query. And the way this is done is through several means. Several ideas are done, but now mostly what are called multi-vector neural information retrieval. And the basic idea here is that you have a bunch of documents that you want to index, and you compute something called document embeddings. And the idea is these things are pre-computed, you have them available, and then you type in a query in Google search box, and that query also gets translated into something called a query embedding. And then you look for the similarity of the query embedding and the document embedding, and then you pick up those documents that are close to the query embedding, and whichever has the highest similarity score, you pop them up as the results for the query that you typed in, okay? And the basic philosophy here is that through natural language processing, and you basically get the gist of documents, what the documents contain, and what the query is asking for, and somehow these embeddings in this space, vector space, relate to each other, and this similarity in the embedding space results in getting good candidates for the search query you have given, okay? And the way this is proceeds is given here in this boxes here. So you type in a query, the query gets encoded, and I'll talk about how this approximate neighbor search gets done, because you have lots of documents. You can't be searching for all of them, so you need to quickly figure out what are the likely candidates. And then from those candidates, you get the detailed embeddings, you do compute the similarity score, and then you give the documents to this user, okay? Okay, so here is how the approximate neighbor searches works. So when you pre-computed the documents, you compute them into this vector space embedding space. And what happens is all of these embeddings, originally when BERT was created by Google, Google used something called 768 for some reason, vector space dimensions. But now these things use up to 4K dimensions. So each of this query, even though I'm showing you here in a planar graph, is actually in 768 or 4,000 dimensions. And what you do is to take all the documents you created for these embeddings, and you create a clustering means. You just do some kind of K clustering. And so what I'm showing you here is in this diagram here, there is a cluster 1, and cluster 2, and so on and so forth. And you have a central candidate to represent this cluster. Okay, so what you do is you create all these embeddings, and for each of this cluster, you take a centroid or mean element, and then you create that as a way to figure out what this cluster represents. And when a query comes in, what you are trying to do is to look through this cluster of candidates and find the first candidates that closely match this query. And what you do is once you have the match of those queried clusters, you go into the clusters and actually find the documents that are necessarily relevant, and then you rank them, and then you bring those documents out to show to whoever is asking for this. Okay, okay, so in order to do all this quickly, typically what information retrievals do is to create something called inverted indexes, and you store these inverted index in memory and try to use them as efficiently as possible. Okay, so just to give you an idea here, so the table here is showing you two sets of approaches to doing the document queries. The traditional way of doing things are in the top level, which you see here, the indexes are roughly less than 2 gigabytes. But with this, I can't move here, okay. With the multi-vector models, you see those indexes sizes are now in several gigabytes per each of these approaches, okay. BERT version 1, which was created originally by Google, and there are a bunch of optimizations afterwards, but the original one had 154 gigabytes of index for this macro data set, which is up at 3.3 gigabytes. Okay, now what you're trying to do is use this in a memory system like this. All of you know how the memory hierarchy works. You have a GPU caching system that has very few memory megabytes. And then if you're using GPUs to use this, GPU's high bandwidth memory is the next to the GPUs. And then you go to system memory, sometimes use the system memory with the CPU memory as a backup for when you're running out of HBM. And then eventually get to secondary storage in order to get things done. Okay. At least when we started looking at this problem, the access that we had for the GPU we had was about 28 gigabytes. And now you can buy, if you have money from NVIDIA, you can buy a GPU which has 80 gigabytes of HBM. But right now, let's assume for the time being, we're limited to 25 gigabytes of HBM. Okay. So if your index has anything more than 25 gigabytes, it's not going to fit in the GPU's high bandwidth memory. And in order for this to be indexed, you'll have to take the help of the system memory. And even with that, let's say system memory is about 128 gigabytes, you're now straddling these index sizes that I showed you are getting to be larger than the memory that's around there. And the idea is, how do you manage this in a system like this, okay? Okay, just to clarify one more thing, is that the way this thing works, let me back up a little bit. The indexing has, as I mentioned, when you do the documents indexing, you do two things. One is you compute something called a CLS index, which basically represents the whole document as one thing. And then you also compute something called bag of word index, which is, again, another representation of the document, but you basically take something similar to a paragraph at a time, and then you index the paragraph at a time to represent the document. Okay. So this index that I talked to you actually has two components. That's the thing. Okay. All right. So the whole idea is to how do we reduce this? People have looked at various ways of looking at this. Primary thing is to reduce the size of these models. And as you see here, original one had 154 gigabytes. Over time, people have been able to reduce that down to something smaller. And this is by basically reducing the number of bits that you use to represent the dimensions and throwing away what they think is non-essential bag of words, indexes, and so on and so forth. But you lose a little bit of accuracy as a result of doing these things. Okay, so what we wanted to do was, at this time when we were looking at this, was could we move some of this to secondary storage and reduce the pressure on memory and not having to put everything in memory? That was the question we were trying to figure out. And the reason for doing this was that both the GPUs have come up with something called GPUDirect storage, which was before, when you wanted to move data from SSDs, you had to first move it to the CPUs, and then only move the data from CPU to the HBM in the GPU. So it actually had to go through this hierarchy. Now with the new GPUs, you can directly move the data from SSDs to HBM to make this a little bit less painful and more efficient. So the idea was could we take advantage of this GDS and move the data from memory to storage and reduce the pressure on memory. That's the motivation for this work. Okay, so far the problem, okay, so here is just an example. We did this just to give you an idea of what happens. In this example, the index was about 20 gigabytes, and we did here with 30 gigabytes of memory, everything fits in. You get done in 45.6 milliseconds, the query latency. But when you constrain the machine to 10 gigabytes, the intent was we were trying to see what happens if I could do this on a desktop, for example. There are two ways of doing this. One is I could put this simply on an SSD and do effectively mmap those. And then whenever I need something through memory accesses, I can get the data through mmap. Other thing is to use traditional techniques for paging, and then say if you could use paging back and forth between those things. And you see what happens when you use mmap or paging, the latencies blow up. And so they get to 183 milliseconds and 76 milliseconds and so on. And so our solution tries to keep the latency the same and while using the SSD, and that's the story I'm going to tell you, which is that I'm going to get to this similar to as cached latency nearly without having to have so much memory as 30 gigabytes of memory, okay? Okay, and how do we do this? The basic idea here is that, we'll just go back one more time. Okay, so when you get a query here that's shown in the dark, we're looking for clusters around the query which are close by. And then you're picking what are called potential candidates that are likely to be the answer to this query. And then you go through a process and then see maximum similarity and then return the documents that have the maximum similarity. So you're making basically picking up what are called candidate documents. So typically what happens is in order to get the results you want, you choose, let's say you're going to come up with 1,000 candidate documents, and you're going to go and evaluate those 1,000 candidate documents to see which one is best represents the query. So that's basically what the pipeline was showing you earlier. So what we do is instead of visiting all of the clusters and then figuring out what to do with the documents, so what we do is break up visiting the clusters into two pieces. We visit the delta, whatever the delta number is, and then the remaining clusters, lambda, are visited in pipeline. And after we visit the delta clusters, we have a set of candidates from the delta clusters that we visited. I'm going to assume these are the best candidates, run with them in parallel in terms of fetching them through I/O, okay? And on the top, I'm still computing, going through the index and computing what is the likely candidates documents. So basically, I've broken up computing the document candidate selection into two pieces. 10% of the thing that gets done, immediately I take the 10%, assume they are the best candidates. I'm going to go issue the I/O for those. And the remaining 90% are getting done while my 10% of the candidates, I'm doing the I/O at this time, okay? And the idea is that now I can overlap the I/O for that 10% of the documents with the computation of the rest of the 90%. And if I'm lucky, at this point, this 10% is the best 10%, in which case I have the results by the time I computed them, and I can give you the results what you needed, okay? Okay, sometimes this may not work out, then I may have to go and fetch the documents that are missed, and that's the part I'm showing you here, calculate the missed documents and fetch those documents if needed, okay? Okay, all right, so each of this here is the contribution that my students made. Basically here, we were selecting the prefetching. This is basically we're prefetching the documents that we're going to prefetch. And then we're using the GPUDirect. This is a new feature so that we can move the data directly from SSD to GPU. And my student optimized some of the the kernel for CUDA to make things a bit faster. And then we compute the early re-ranking to reduce the ranking latency. Okay. Okay, we do all of this and hope that we can manage to do this. Okay, so just to give you an idea here, this data is showing you, so you can compute what is available based on the computation cost of the indexes and computation cost of the latency of fetching the documents, what is the size you have. But this thing is showing, these indexes use something called nprobe. Nprobe is the number of clusters you're going to query to see if they're close to the query that you're looking at. And basically, as you increase the number of probes, on the y-axis is the recall at 1K, which is basically telling you how likely you're going to get the document. It levels off after a while. Okay, so you can trade off this for a bit of a room to get what you need to do. Okay. Okay. This is showing you what happens if you change the prefetch step. What is the likelihood you're going to get the hit rate? How many documents are you actually going to need? What are you going to get in that prefetch? And you see here for most of these two data sets we've used to call MS Marco 1 and Marco 2, if you use about 10% of the documents to probe, you're getting about 80 to 90% of the hit rate, the accurate documents. Okay, so the prefetch hit rate is very high. With 10% of the things, you get most of them. And for the 20%, 10% of miss, I'm going to allow for that latency in the back that I showed you earlier. Okay? Okay. Okay, so here is a story, which is, if you see here, for the set 2, the bag of words index is 255 gigabytes. So there's no way you will be able to put this 255 gigabytes in memory. So we store all of this on the storage, and there is a CLS. This is the only index that we're going to leave it in memory. So we're reducing by a factor of about 1/9. This is the total index size is these two together. So we're basically keeping about 1/9 of it in memory. The rest of it stays in the SSD to move things around. Okay, so here are the results quickly. As you see here, this is for the set 1. We vary on the x-axis on the table 10 gigabytes, 15 gigabytes, 20 gigabytes, and so on, the amount of memory that's available. With 30 gigabytes, everything fits in memory. So nearly they're all about the same. But as you see here, as you reduce it here, ESPN maintains what is basically best possible thing at the bottom, even with different amounts of memory that's available. Okay? And the story becomes easy to see here. If I have this with the Marco version 2, this one is as the 256 gigabytes is what you need to store everything in memory, more than 256 gigabytes. And as you reduce the amount of memory, the other approach is basically the things quickly blow up. Okay? Whereas with ESPN, we nearly maintain the same amount of same latency across different memory configurations. Okay, so there's a whole bunch of other ablation studies to show. I'm going to skip this in light of keeping you guys here from going and getting some rest. So I'll just show you this, which is we have done a bunch of things here to get the performance. So if you take the data from virtual memory, the latency is 76 milliseconds. And instead of using virtual memory, you use GPUDirect storage. And so that knocks it down from 76 to 58.3 milliseconds. So GDS is bringing that gain from 76 to 58. We use the custom CUDA kernel that reduces the latency by another 4 milliseconds. The prefetcher reduces it by another 6 milliseconds. Early re-ranking reduces it by 2 milliseconds. So this is giving you where the gains are coming from. And so this is basically go from 76 milliseconds to 46 milliseconds through various stages of things that we've used in here. Okay. Okay, so there's obviously some limitations here, what we have done. There's still a bunch of work to be done. First thing is we've used a single SSD here. Obviously, when the data is striped across multiple SSDs, we would have to worry about the striping and making sure there's enough bandwidth. Other thing is as the size of the documents grow, the bag of word sizes can grow. We have to look at what happens as the document size grows. In fact, we would assume this approach should provide a better solution because as the data size grows, we should see more of an improvement. And we have done something for bandwidth to make things bandwidth efficient. I didn't talk about it because of time, but there's still some work to be done to making this more bandwidth efficient. Here is the conclusion. Basically, we have found a way to optimize the pipeline for data retrieval so that bulk of the index could stay on the device and be efficiently retrieved by overlapping computation and the I/O retrieval by basically prefetching 10% of the documents. And those 10% of the documents that are prefetched seem to be most of the time the correct documents that we're prefetching 90% of the time. So we gain benefit by overlapping things. And we've reduced the storage cost, storage and memory requirements by about a factor of 8. Thank you.
Thank you. Questions? Yes?
Yeah, interesting work. I might have missed what you already covered. Is there any some accuracy evaluation? Because
yes.
you talk a lot about this.
All of these are at the same level of accuracy. So in fact, these results here are produced at the same accuracy here. Okay, in fact, embedding latency. So so there are two parts to the paper. First part was not sacrificing any accuracy at all. Okay, so those results that I showed you, oops, I don't know what happened here. Where are the numbers? These numbers are all at the same accuracy. Okay, so we have tried to make this, we have looked at potentially sacrificing the accuracy here in order to make the things faster, and you see the loss in performance you could lose. So if you re-rank 256 documents, you're not going to lose any accuracy, but potentially what you could do is to reduce the number of rankings you want to try out, and if you reduce it to, let's say, 64, you are going to lose some accuracy. Okay. So that depends on how many documents you're able to retrieve. So if you only have bandwidth to, if you have bandwidth to get the 256 documents to re-rank, you're not going to lose anything, but if your bandwidth is only 64, then you would lose the accuracy by doing this.
All right, thank you.
Okay.
Any other questions? Okay, if not, then thank you once
Thank
again.
you.